Whoops. All right, so people watching the video is going to miss the first question. Although based on the triviality of this question, I don't think they missed anything. Yes, F in chat. So that is 3A, trivial. 3B, it's not a subspace. You're trying to prove that the set contains all the linear transformation that go from R5 to R4, whereas the dimension of kernel of T is less than or equals to 2. It's not a subspace. If you compose two functions, you just look at how can you compose two functions with a kernel of dimension 1, but suddenly the composition of them have kernel of dimension 2. Right? So for you can think of a map that go x1, x2, x3, x4, x5, and you map that to 0, x2, x3, x4, x5. This will have a kernel of dimension 1, so you call this T, and then you can call the next one X, which is x1, x2, x3, x4, x5, and now you map it to x1, 0, x2, x3, x4, x5. No x5. x3, x4, x5. Now, T composed with S have a kernel dimension of 2. And you just need to prove to me why that's the case. And that's enough to prove that it is not a subspace because it is not contained, right? It's not closed under a composition. So, sorry, map to R4. What am I talking about? Map to R4. There, map to R4. Perfecto. Right, you compose the two of them together, you get a kernel of dimension 2. Right? Yeah. Why do I have a phone call right now? I'm going to assume it is a spam call. What they should have known is that I do not pick up phone calls, so for anybody that call me, I do not know them. Because everybody knows me, know my phone number, knows that I never pick up phone calls. So calling me is possibly the worst option that they can do. Explain again. Right, we're looking at T. We're looking at this. First look at this linear transformation. We can all recognize that S and T is basically the same thing, right? With just a shift to 0, but in the end, they're the same. So this is a map from R5 to R4 without this X5 at the bottom, which I was dumb, right? So from R5 to R4. What is the kernel of this T? Kernel of this T contains all of the vectors in R5 such that we want every one of these to be 0. We want this entire thing to be 0. Well, x1 is mapped to 0. So I guess, God damn it. Should not have done that. I have just figured out what my problem is. This is actually the kernel dimension 2. Let's call this x1. Let's call this x2 and this x5. There, that'll do. I have made a grave mistake. Yes, so the kernel of this would be every single one of these that gets mapped to 0. So that means x1 needs to equal to 0, x2 needs to equal to 0, x3 0, x4 0, but x5 can be anything. but x5 can be anything. Right? And of course, the dimension of this kernel is the number of variables that can be anything, right? Which equals to 1. So this, then we know that T is within the subspace. Similarly for S, right? S, the only free variable is x4. x4 does not get mapped to anything. Therefore, when we're mapping everything to 0, x1 needs to be 0, x2 needs to be 0, x3 0, x5 0, but x4 can be anything. So you know that the dimension of kernel of T equals to 1 as well. Now, the combination of these two, oh, not combination. Fuck, what am I meant to do? What am I meant to do again? I forgot. Is it composition? No, it's not composition. It is plus. Why did I think of composition? We're not looking at a group. It's T plus S. So this will be x1 plus x1, x2 plus x2, x3 plus x3, x4 plus x1.
Never mind.
Okay, so all of them will be 0. x4, x5, 2 satisfying a linear equation. Ooh. T plus S is also of kernel dimension 1. Yes, what's up? You can use your mic, I'm listening.
Null of T needs to be greater than 2, though.
It's the one from 2 to 4, right?
Yes.
How many people do you have?
10? Still 10?
They say there's 4.
They can just go to Quarkus and go for, what's it called? Quarkus and do the collaborate thing. Yeah. What am I missing here? This is not a dimension, kernel of dimension 2. What is your question? You don't want to speak? I cannot.
The null of T needs to be greater or greater than 2.
Yes, I'm just looking at.
But
Is anybody saying anything? Because I cannot hear anything.
F.
I have 2 people raise their hand up. Yes, because I have done this question terribly wrong. I'm still looking at so kernel of dimension 1, and then somehow added them together as of dimension 2. Well, if that is not a subspace, that has to be the way. You add 2 together, and then it's no longer the same kernel because okay. So what I'm going to do is I'm going to do this, but instead of x5, I'm going to change it to minus x4. If I change this to minus x4, what do I get? T plus S equals 2. So T plus S of x1, x2, x3, x4, x5 equals 2. If I add these two together, I get 2x1, 2x2, 2x3, 0. Yes, and this has a kernel of dimension. So the kernel of T plus S equals to all of the x1, x2, x3, x4, x5s. So x1, x2, x3, x4, x5 in R5. Right? Such that you have x1 mapped to 2x1. In order for this to be 0, x1 has to be 0. Similarly for x2, in order for 2x2 to be 0, x2 has to be 0. Similarly for x3, in order for 2x2 to be 0, x3 has to be 0. 0 is already 0, don't care about it. x4, x5 are free variables. So x1 equals to x2 equals to x3 equals to 0, whereas x4, x5 are free. Right? And this entire thing has dimension 2. There. I'm just not dumb. I'm just slow. I'm just slow. Okay, let me re-explain everything. This is yes, my problem. Okay, so what we have is the following subspace. So what we have is the following subspace. Let's give it a name. I don't know, U equals to all of the linear transformations that go from R5 to R4 such that the nullity the dimension is greater than 2. Oh my God. Oh my God, I'm so stupid. It's greater than 2. Yes, that is a greater than sign. That is a greater than sign. This is a greater than sign. Yes, it is a greater than sign. Okay, you guys can stop laughing in the chat now. Okay. But this makes it even easier. Okay, so let S and R come from U, and let's define. So basically, let S that go from R5 to R4. This is even easier, such that it maps x1, x2, x3, x4, x5 to, well, I'm just going to do like x1, x2, 0, 0. And then for R, it maps from R5 to R4, such that x1, x2, x3, x4, x5 gets mapped to 0, 0, x3, x4. This has a kernel nullity of S equals to 3. Right? The reason why the dimension of the kernel equals to 3 is because you have x3, x4 free, and x5 free. Right? x3, x4, x5 can be literally anything. The only thing that is not free is x1 has to be 0 and x2 has to be 0. Everything else is the same. They're all free. So the dimension equals to 3 because there are three free variables. Similarly, x3 and x4 are fixed in this case when you want it to be 0, right? You want x3 equals to 0, x4 equals to 0. But then again, x1, x2, and x5, they're all free. So we know that the nullity of R is also 3. But if we add these two linear transformations together, which I do not have space to draw that out, let's just do this. But if I add these two linear transformations together, so I have S plus R, right? What I have is x1, x2, x3, x4, x5 gets mapped to x1, x2, x3, x4, like that. And we know that the nullity for this of S plus R equals to 0, equals to 1. right? And the reason for the sum to have a nullity that equals to 1 is because in order for this to be 0, x1, x2, x3, x4, they all must be fixed to 0. So the only thing that you can change is x5. That means your nullity is 1. So you have 2 of the elements in this subspace. When you add them together, it is no longer in the subspace because the dimension of the kernel is 1, which is not greater than 2. Yeah, see, the moment that I can read the question, I can just do it. I'm not totally useless. I'm just sort of incompetent. It's okay. Yeah, so x5 is the thing that is free because x5 is not being mapped to anything. So if we set every single one of these to be 0, that means x1 to x4 has to be 0. Well, what can x5 be? Well, it doesn't matter. Right? x5 can be like 720, 89, 727, and it'll still be mapped to 0, 0, 0, 0. Right? Phew. Okay. We'll go with that. We'll just pretend that I did not make a catastrophic failure. For C, so suppose W and V and W are finite dimensional vector space. Let V being V, let E equals to all the linear transform. Okay. Show that E is a subspace of L. It is so easy though. I have been bamboozled by the useless thing that is called technology. Okay, so that's 3B. I don't know too much. I don't know if I want to do 3C because it's another one of those prove something's a subspace type of thing. We've done that like a million times. I don't think I want to do it ever again. The thing that is most important regarding like proving things in linear algebra is actually you need to, right now, the biggest problem I see in your proofs is just that it doesn't have a proof structure. You need to have a structure in your proof. What is something that you're given? What is something that you're looking for? What are some assumptions that you can make? What are some assumptions that you cannot make? Right? You cannot just say, oh, A is true because A is true, therefore A is true. I've seen that type of argument, circular reasoning. Kind of triggers me a little. And if any of you want to say something, you can just say by unmuting your mic.
Raise your hand.
I'm not going to be closely monitoring the chat that well in order to allow them to raise their hand or anything like that. Oh, we have 19 people. Look at that.
So popular. Holy.
Did we miss anything?
Yeah.
Okay, it's working now.
Sweet. Hopefully it is working.
Get rid of the alarm.
Okay. Yes. So before we have problem, now we had the problem. Let's hope that we will not have problem. This is the last time that we have problem. And for 3C, 3C. Part A, show that it is a subspace. I'm just going to skip it. For 1, I'll give you a hint, which is these two sets, range and kernel, right? You want to prove that they're equal. Sorry, you want to prove that they are not equal. Well, both of them are subspaces, and they cannot be equal if they have different dimensions. So the dimension of range, or the rank of T, does not equal to the nullity of T. Is it T? Yes, it is T. If their dimensions are not equal, that means they must not be equal. Right? Because they're both subspaces. And if subspaces equal to one another, then their dimension has to equal to one another. if they do not equal to one another in terms of their dimension, then they cannot equal to one another, right? Can I just write a tad larger? Yes, I will. Right, so you can just work from the dimension point of view. And what is the dimension point of view? Well, consider the rank equation. Which states the following: the dimension of the domain equals to the rank plus the nullity. Should be a 2-line proof for this question, or maybe 3 lines. Right, so if they have different dimension, then that automatically means that they cannot be equal because of the fact that they are both subspaces. Right, if they're not subspaces, then it doesn't even make sense to talk about dimension. Well, what is a dimension of something that is not a vector space? Right, it doesn't make any sense. All right, so that is for 1. And for 2, I don't know why people are having so much trouble with 2. All you have to give me is an example of a linear transformation whose range equals to the kernel for R4. Well, from the rank equation, obviously you should be able to tell that the dimensional domain equals to 4, and range has to equal to kernel. That means rank and null must both be 2, right? You have a dimension of a range that has to be 2. The dimension of the kernel has to be range of 2. Well, you are looking for a linear transformation that maps things to the kernel, right? You're looking for a linear transformation and map the range of T to the kernel of T, right? So one person on the WeChat group did suggest a corollary, which could be useful to check whether or not if your transformation is a correct one, which is the following. If this is true, that implies that T of x must equals to 0. The converse does not work, by the way. The converse does not work. Okay? The converse does not work. Just because you have a transformation such that you compose with itself gives you the 0 mapping, doesn't mean that range equals to the kernel. However, if the range does equals to the kernel, this must be true. So you can use this to check if you got a wrong answer. If this is not true for your transformation, then your answer is certainly wrong. Right? So basically, you are mapping x1, x2, x3, x4. Right? You are mapping x1 to something, you're mapping x2 to something, you're mapping x3 to something, x4 to something. So you have to map 2 of them to 0, right? Because you have to map 2 of them to kernel. And then for the other 2, you have to map to where the kernel is. So for the other 2, you have to map to where the previous 2 are. Should be pretty obvious. One example at the very least. There are a million examples for that. Okay. So that is for 3C, everything, I believe. Yeah, that's for 3C, everything. And for D is, I think I have given you the answer for D for assignment 3. Assignment 3, last question. I thought it was never going to appear again, but apparently it did appear. So for question 3D, I did give you the answer already. For E, again, I did that during the tutorial, the proof of first isomorphism theorem. If you have any questions, you can just refer back to the notes. Do any of you need me to prove that thing again?
I do.
The first isomorphism theorem?
Sure.
You know what? If you want to learn how to prove that, take CO1.
CO1.
Yes, math CO1.
What's the name?
Group theory.
No.
Yeah. It's abstract algebra. Everybody loves algebra. Algebra is the best.
Group theory.
Group theory.
Isn't that just like a more advanced version of A67?
No, group theory.
Group theory.
Group.
I heard group theory.
No, group. Golf, Romeo, Oscar, uniform, Papa. Group theory. Not proof theory. Proof theory. There is a proof theory. It's called a mathematical logic. Math CO9. So if you want to take a more hardcore version of A67, you have a choice. Groot theory. Groot theory. Question 4. Guys. Question 4. Yes, it is quite literally a 5-minute job. I do not think I need to do question 5 at all. You find the determinant of a squared. Well, a squared is just a times a, right? What's the determinant of a times b? Right, and find the determinant of 3a, right? And find the determinant of a plus a. Well, a plus a. That's a trick. That's a little trick. Determinant of a plus b does not equals to the determinant of a plus the determinant of b. Okay, so for C, you have to be careful a little bit. Although a plus a, there is another name for a plus a. 9a. Yes, a plus a equals to 9a. You are correct. How about A5? So in terms of the preparations, I have only looked through the determinant stuff. I do not think Kylie have talked about eigenvalues last week. Now, he might have started to talk about eigenvalues this week, but up until last week, I do not think he talked about eigenvalues. So if you want some information on eigenvalues, I guess you can go to the Friday one. But for now, for this week, I don't think I'm going to go over anything in the eigenvalues. But in terms of determinant, sure. Is determinant of 3a equals to 9 determinant of a? No. Does a plus a equals to 9a? Yes, but slash s. I mean, it depends on like what 2 does 2 times 1 equals to 9. A is 3 by 3, so yeah. And so for determinant, the only situation where determinant makes any sense, the only situation where determinant makes any sense is when you're looking at a square matrix, right? If it is not a square matrix, determinant does not make any sense whatsoever, right? So what determinant does is it takes a whole bunch of vectors, right? If we have determinant, if I have matrix A as the following, I have A1, I have A2, all the way to AN. Let's say that this is a square matrix, so AN by N. The print is a little bit too small. Right. Then what do you have for the determinant, or just that of A? You get a single number. And what that number does is it looks like at every single one of these vectors. Maybe you have your A1 here, maybe you have your A2 here, maybe you have your A3 here, and I look at the shape that is actually has a very funny name. So this has a shape like this. This has a shape. Drawing it is a little bit difficult, but what it does is it forms something called a parallelopotent. Right. So like if you have 3 different lines, in 3 different directions, then what you get is you can, from those 3 lines, you can generate a parallelepiped. It probably makes more sense in 2D, where you have a vector 1 and you have vector 2, right? You can generate a parallelogram right here. Right, in 2D, it's called a parallelogram. Whereas in 3D, it will generate something that is similar. And then for this one, I have to draw this direction, I have to draw this direction. And then for this one, I have to draw this direction and this direction. Somehow forming oh my God. You know what? This just looks like pure garbage. How do you draw a parallelepiped? It doesn't matter. Just, you know, it's just a parallelogram. It's a parallelogram, right? That is shifted by another parallelogram. Defined by your 3 vectors right here. This is a parallelepiped. Right, that's what determinant is. It is just looking at the volume. In this case, it is looking at the area. In this case, it is looking at the volume. On the 4th dimension, it is looking at, well, volume. From the 3rd dimension onwards, everything is just called volume. Or another way would be you are looking at the measure of the shape that you just created, the shape that you uniquely define by these 3 or by these n vectors, right? Because n vectors together, you have uniquely defined some sort of a shape there. So in terms of 3 vectors, you can uniquely define a parallelepiped. For 2 vectors, you can uniquely define a parallelogram. For 4 vectors in 4D, you can define a 4th dimensional parallelepiped, and so on. So these number of vectors, they define a unique shape. And when you have a unique shape, especially it is closed, since all of the vectors have finite length, right? So it is a closed shape. It makes sense to talk about the measure of this shape. It makes sense to talk about, well, how do I compare shapes? How do I quantify shapes? How do I use a single number to represent some characteristic about the shape? And that's kind of what determinant does, because what determinant of a 2-dimensional matrix, it talks about the area. For 3-dimensional, talks about the volume. For 4th-dimensional, talks about the 4th-dimensional volume, and so on. So that would be the measure. The way to calculate determinant is a very annoying one. Determinant could possibly be the most annoying thing that you can calculate, aside from row operations. I don't know, maybe row operations is more annoying. So the way to calculate determinant, I think all of the computer science students rejoice. Is something called a recursion. You have to do it recursively. So the first thing is the determinant of n equals to n. So this is for all n in the real numbers. If we're looking at a determinant of a 1-by-1 matrix, which is just a number, if we're looking at a determinant of just that, well, the determinant of a 1-by-1 matrix, matrix is literally just n. And it kind of makes sense too. If I'm looking at a 1-dimensional space, which is just a real number line, starting from 0, right? Then the magnitude of the vector n is just the length. And what is the length of the magnitude of the vector n? Well, n. Right, so the measure for this is just going to be n itself. Now, this is the only easy part. So in order to move up to higher dimensions, we have to define something called a reduced matrix. Not a reduced matrix. Actually, yeah, reduced matrix, I guess. Maybe. Right, so basically, if I have A, if I have Aij, because it is capital letter A, you know I'm talking about a matrix here. This equals to the original matrix A with the ith row and jth column removed. Okay? So if I write out a matrix with a subscript, it does not mean the specific element at that subscript. If I mean a specific element, I'm using lowercase aij. That means a specific element with that subscript. But if I'm talking about the entire matrix with ij as a subscript, then I am talking about the reduced matrix with A removing the ith row and the jth column. So an example, right? So if A equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Then A22, right, will just be 1, 3, 7, 9. Right, A22, I remove the second row and I remove the second column. I'm only left with these 4 numbers. Right? And yep. And then A13 would equals to, I remove the first row and the third column. So 4, 5, 7, 8. Right, so this is an example of what a reduced matrix is for.
Weird notation, like you're saying determinant of n equals n.
Uh-huh.
Is that right?
Yeah, for n being a real number.
The determinant of
A real number is a number.
Okay, I thought that was a matrix.
No.
Yeah.
Matrix, we usually use capital letters. Right. So that is that. And the way that you calculate the determinant, now you know the base case. So recursion is basically just induction. Now you know the base case. Let's see how you calculate the 2x2 matrix. Actually, you know what? Let's just give the general formula. Determinant of A of size n by n equals to so the way that you do it is you choose any row or any column. It does not matter which row and which column that you choose. So for this case, let's just choose a column. Okay, so let k be a number between 1 and n. So I'm going to choose the kth row. Then this equals to the summation of -1 to the power of I, determinant of A with some kind of subscript. So k is the row, which is fixed. So I have to remove the kth row. And the column will go from 1 to n. This way of calculating determinant is not exactly it's not exactly obvious why that's the case. You want to call this a cofactor? Yeah, you can call this a cofactor. I guess the reduced matrix has it's a little bit confusing with REF. Doesn't really matter. With yeah. So the way that you calculate it is you choose any row, doesn't matter what row it is, choose our favorite row, or the best way to do it is to choose the number of row with the most number of zeros inside of it. And then you're just going to cycle through every single one of the column, calculate the determinant of the matrix without the row and the column, and then put a -1 to the power of that in front, in the front. So an example. So if we're going to calculate the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, what I do is I pick any row. In this case, any row doesn't really matter because none of them have a 0. So I cannot really save any step. So I pick any row. Let's say I pick the second row. If I pick the second row, then k equals to 2, right? What I have in the end was j going from 1 to 3 because this is a 3 by 3 matrix. So n equals to 3 minus 1 to the power of j times the determinant of the matrix. I forgot to give it a name. 1, 2, 3, 4, 5, 6, 7, 8, 9. Removing the second row and the jth column. Right? So this will equals to. Now if I plug in j equals to 1, what do I get? Wow. If I plug in j equals to 1, this becomes 2. So this becomes 2. So this is just 1. I don't care. The determinant of this. So I'm looking at minus 1 squared determinant of this matrix without the second row and the jth column. So j equals to 1 without the second row and the first column. The determinant of 2, 3, 8, 9, plus, now j equals to 2. So I have minus 1 to the power of 3 multiplying by the determinant of, again, this matrix without a second row, without a second column. So I'm looking at 1, 3, 7, 9. Right? And again, plus minus 1, j now equals to 3. So to the power of 4 times the determinant of, so this is 2, 3 now. Removing the second row and the third column, I'm left with 1, 2, 7, 8. So it's going to be the same for every single determinant. If you have an n by n matrix and you want to calculate the determinant, you are going to break it down into n of n minus 1 times n minus 1 determinants. So the number of
You screwed up.
Where?
You have to multiply it by whatever value, right? So you have to multiply it by 1, 4, and 7.
Yes.
But you didn't do that.
Did I not do that? I did not do that. Why am I? Oh my god. This is what happens when you don't sleep.
How do you even notate that formula?
Huh?
How do you even notate the formula to do that? Like,
Oh, how do I notate the formula? Easy. This is what you do. Multiply by a k.
oh yeah, yeah, yeah.
This is so much work. Multiply by a 2j. Oh, I don't even have enough space for this.
You should have picked the row 1. Because it's the smallest row, right?
Well, yes, but in the end, it doesn't really matter.
Yeah, it doesn't matter.
Because if you pick the smallest row, then when you calculate these determinants, they're going to be bigger numbers, right? So this is plus 2. No, not 2. I chose the second row. So this is 5. And then this is plus 6. I should not have drank so much coffee in the past 2 days and not sleep. I should have slept. I should have slept.
Well, then move the board up because we can't see.
Sorry?
Move the board up because we can't see. Because the podium is blocking your camera. There you go.
This is why I need someone to be there. Yes.
Yeah, they'll be your audience.
It's okay. Nothing of a value was lost since I made so many mistakes already in the beginning of the tutorial. First, by reading what? By reading the less than or equals to, by reading the greater than symbol into less than symbol. And now I have no idea how to calculate the determinant.
Here, I'll finish the determinant. How about that?
Okay, finish my determinant.
Let me get a calculator. You learn how.
You do not need a calculator for this.
So it's gonna be 6.
You do not need a calculator for this.
Is it easier?
Here.
Let's try. Alright.
Yes.
For this. 4 of 18 minus 24. That look right? 18 minus 24 plus 5 negative 1 9 minus 21 plus 6 8 minus 14. Okay. Now this is 4 of negative 6.
Okay.
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 Minus 5, 9, 11, 12. Negative 12.
Okay.
Okay. Plus 6, negative 6.
Okay.
Looks good. Equals negative 24 x. Negative 24 plus 60.
Okay. Yes.
Minus 36.
Okay.
And what? This is 50, 60. Okay, this is just 0.
Yes, it is 0.
Nice.
They're linearly dependent, so it has to be 0. So yeah, without doing this, I can already tell you what the determinant is.
You might want to like just clarify how I got
Yeah. That's what I'm planning to do. That's why I'm just going to do this and bye.
No.
You do not get to see this. Because he just skipped like 7 different steps, and we do not want that, right? This is not allowed. This is not allowed. So, what would you use? What kind of uncivilized person are you? You use the back end of the chalk.
PowerPoint and presentations.
Uncultured people, man. Uncultured. Uncultured. Okay. So from here, we have to work out what each one of these determinants are. And work out each one of these determinants. So let's begin with working out the first determinant, which is the determinant of 2, 3, 8, 9. Right, we're going to use the exact same formula. We have to choose a row. Well, in this case, let's choose the first row, because it doesn't really matter which row that you choose. They're equally as not good. So let's choose the first row, right? And I'm going to plug in back into my formula. I have minus 1 to the j plus 1. So the first one is just minus 1 to the 2. Multiplied by the determinant of removing the first row and the first column. So I'm left with 9. Right? Times the value for the first row, first column, which is 2, plus, now j equals to 2. So for this, I have selected that row equals to 2, row equals to 1. Right? So now j equals to 2, so I'm left with minus 1 to the power of 3, which is j plus 1, multiplied by the determinant of removing the first row, second column, which is 8, and then multiply by the value at 1, 2, which is 3. Right? So what is this equals to? Well, again, we're looking at now determinant of a single number. The determinant of a single number is just the number itself. So we're looking at minus 1 to the power of 2, which is just 1. You can ignore that. We're left with 9 times 2 plus minus 1 to the 3. Well, minus 1 to the 3 is minus 1. So there's a minus here. Determinant of 8 is just 8 times 3. Right, which equals to 18 minus 24, which equals to minus 6. Similarly, the determinant of our second matrix that we'll have to calculate right here, 1, 3, 7, 9. Right, this equals to, so I'm going to select, again, I'm going to select the first row. So k equals to 1. So this is minus 1. To the j plus 1, j equals to 1. So this is 2 times the determinant by removing the first row, first column. So I'm left with 9. Multiplying by the first row, first column. Multiplying by the element at that location, which is 1. Plus minus 1. Now j equals to 2. So this will be 3 plus 2 plus 1 equals to 3. Multiplied by the determinant of removing the first row and the second column. So I'm left with 7 multiplied by the value of this number here, which is 3. So this equals to determinant of 9 is just 9 times 1 minus 1 to the power of 3 equals to minus 1. And now I have 7 times 3 here. Right? So this equals to 9 minus 21, which is minus 12. Yeah. You have problem? What problem do you have? Did I make another mistake? Too long. Well, next time I'll just give you a 4x4 determinant. Why don't you just compute in your head? It's not long, it's fast. Right? And then, of course, the determinant of the last one is 1, 2, 7, 8, which I'm just going to skip. This is going to be what? 8 minus 14, which equals to minus 6. Right? After you computed all of these determinants, that's when you can bring these values back into your original expression and get this as your final answer. Although we all know that this is pretty ugly. The person who wrote this should really practice their handwriting on writing on the board. So we'll just slide that up. Pretend we've never seen it. Symbolab is OP. Yes, Symbolab is indeed OP. Oh, it's an online exam. Yes, it's an online exam. So that means whatever computation question that Kaidi can ask, you just put it into Symbolab. Yes, you can row reduce, right? You can calculate the determinant. You can calculate the inverse. Just one single. You can calculate the eigenvalues.
The problem with that is those calculators now, you can also show steps.
Yes.
Right? So
Yeah.
even if you ask, show your steps, you copy that.
Like show steps, no problem. Right, Symbolab has all the steps got you covered. No problem. Yeah, there is no computation questions. And I actually do not know what he wants with the webcam and microphone because who am I kidding? He is not going to administer an exam and have everybody in front of a webcam and a microphone. Yeah, and then it just like you have, well, we have a lot of TAs, so that is actually not like it can be done, but truthfully speaking, should it be done? Right? Like I do not want to see what kind of disaster it is in your room, right? And then we just have like 20 TAs, And then you just go through the webcam. You just keep on left clicking, right? Webcam, webcam, webcam. It's just like, that is just dumb. Plus, even if that's the case, why does he think that the TA is actually going to be working like catching cheese instead of just putting the screen on some other, instead of just putting the window on some other screen and do something else, right? So I have no idea what he's planning to do, but whatever thing is, just don't worry about it. So that's calculating a determinant. It is incredibly annoying, incredibly tedious. That's why when you are doing calculations for determinant, you always choose the row and the column with the most number of zeros, because you do not have to. If you choose the ones with the zeros, right? Because you have to multiply by the value at that specific element, it will just be 0. So you don't have to calculate anything. So choose the ones with the zeros. Those are the best. And if you can visibly see that there are 2 row vectors or 2 column vectors that are linearly independent, that are linearly dependent with one another, again, you do not have to compute. You can just write down 0. It's pretty interesting because the following fact is not immediately obvious on why this is the case. Why does the following proposition hold? Why does the following proposition hold? So let A be a square matrix. So it is an n by n matrix of A1, A2 to AN. Right? Why is it true that the determinant of A equals to 0 if and only if, I do not like to write the word if and only if. I'm just going to write this. If and only if at least 2 of, I don't even need to write that. I'll just write this. A1, A2, A3, AN are linearly dependent. It is not immediately obvious on why this, not at all, right? Okay, maybe it is immediately obvious if you say that, which is basically the reason, yes. So the determinant of A equals to 0 means these vectors are linearly dependent. And because, as I said, you can start with any row or any column, that means the column vectors are also linearly dependent. Which is kind of strange, because what you're basically saying is that if the row vectors are linearly dependent, then the column vectors are also linearly dependent. If the row vectors are linearly independent, then the column vectors are also linearly independent for a square matrix. Why is that? They're completely different vectors, right? For row vectors, you can shift them around. That will change the column vectors. They're still linearly independent or linearly dependent. Doesn't really make too much sense. And yes, the reason why this thing equals to 0 is precisely because, remember what determinant of A is trying to measure. Determinant of A is trying to measure some kind of a measure. In this case, volume or area or volume, right? If you have a set of linearly dependent vectors, that is the same as saying, well, right? You have let's say in 3 dimensions, you have 2 vectors that are on the same plane. Which why did I choose 3 dimensions? No, 2 dimensions. I cannot draw three-dimensional objects at art. Right? So two linearly dependent R2 vectors means they're on the same line. They're collinear with one another, right? Then the parallelogram that they generate is of course of dimension 0. All of these n vectors, if they're linearly dependent, that means they will generate an object that is not dimension n. And any object in the nth dimension that is not of dimension n does not have a volume, because it is the same as in R3 when we have a flat piece of paper. It is an R2 object, and it does not have any volume. Right? Or for R2, we're looking at a line. Right? R2 is of dimension 2, whereas a line is of dimension 1. What is the area of a line? There isn't any. Right? So in order for these vectors to generate some kind of object in a specified dimension, they all have to be linearly independent. Otherwise, if two vectors exist on the same plane, then they have just reduced the number of dimensions. Okay. And then for properties of determinants, again, I don't know what is it that you do not know about the what is it that you do not know about the properties of determinant? The only reason that I was hesitant to talk about determinant the whole time is because aside from the conceptual things, like what does determinant do? It does a measure of the whatever object that it creates out of these vectors. Or say, how do you compute a determinant? Which is, again, I think is kind of useless. I do not know if there's anything about determinant that is not just readily available online. Right? Like if you go to determinant on a Wikipedia article, and then you look at the properties of determinant, it basically lists all the determinants that you ever need to do, that you ever need to use. Right? Like the determinant of the identity matrix is just 1. Right? Like the determinant of the transpose is the same. The determinant of the inverse is just 1 over the determinant. Right? The determinant of AB is just determinant of A times determinant of B. So I do not know if there's anything about determinant that is not something that is just not readily apparent or available on the internet. And the proofs for all of those properties are also incredibly trivial. So for example, the determinant of the identity matrix I, well, you're just multiplying all of the column, all of the diagonal, which is just 1 times 1 times 1 times 1 times 1, which is just 1, right? The determinant of R times A equals to R to the power of N times A is, again, fairly trivial because look at that. If you multiply everything inside here by R, well, you just multiply here by R. But everything in here you're multiplying by R, and you have this A here. So you're just multiplying R to itself n different times, which is why you have an R to the power of N. Because right here you can factor out R, but only an n minus 1 dimension object, right? So you can factor R from n to n minus 1. That means you can factor another R from n minus 1 to n minus 2. That means you can factor another R from n minus 2 to n minus 3, and so on. How many R's in total? N R's in total. So it's R to the power of n. Like all of these are fairly obvious things that you can convince yourself or to prove. So I do not know if there's anything else about determinant that I should or need to cover. So do you guys have any questions? You can open your mic and speak. Open your mic and speak. I keep on getting notifications. It's so annoying. Actually, since now I have access to CrowdMark, I technically can give you all 100%, but it is almost guaranteed if I do that, I will just lose my job. So You see, it's a little hard.
Well, you're 15 now.
Yes, it was 20 for a little while.
Not bad, not bad.
Well, I guess most of them will just watch it online, so it doesn't really matter. Convince Kaidi to make assignments more weight. So there is one thing that you guys can talk to Kaidi, which I think I'll send an email to as well, or maybe convince them on a WeChat group, because there's this problem with the online final exam. Is because you cannot expect people not to cheat. So a way to reduce the impact, because removing the entire idea of a final is not possible, let's just say, right? We cannot just do no evaluations after the midterm. So we cannot really do that. But if we're going to do an online exam, then people are going to cheat. We expect people are going to cheat. We know that people are going to cheat. We know that people are going to want to cheat. So then there are a couple of ways for us to mitigate that. One of the more controversial ways to make the exam hard, like very hard, so that even when you cheat, it'll take you a lot of effort to do the exam. But the problem with it is the fact that, what about people that choose not to cheat? If you make the exam super difficult, that for cheaters, it is even hard for them to struggle through it. What about people that are legitimate? You are just kind of giving them a giant middle finger for being virtuous, which is not what we want to do. So that left us the option of reducing the impact of cheating. If we know that cheating is going to be there anyway, it makes more sense to say for my DO1 class, one of the options would be to reduce the final exam's weight. Right? So if we know we're going to cheat, if we know that people are going to cheat, so instead of 50% of the final, let's just say the final exam only accounts for 20%. Right? So that the impact of cheating is going to be much lower, and the other 30% is going to put it into midterms or assignments. We can distribute them in whatever way that we wish, right? We can say now midterm, instead of 40%, it's now going to weigh 60%, and assignment is going to weigh, instead of 10%, it's going to weigh 20%, right? So that is something that we can do as well, and I think it is a better option. If Kaidi does insist on holding an online exam, then there really isn't much other option than that, to be honest. So that would be one of the more, I guess, popular option, or more of a fair option. Because we have to strive a balance between people wanting to do something and what is actually fair. So any kind of significant change regarding to the grading scheme needs to be approved both by the university and by something called a GPP, UAGPP. So the University Academic Grading Policy. I don't remember what the last P stands for, but something like that. So basically, the instructor needs to get both the university to agree and the students to agree, right? So in order to get the university to agree, they submit a proposal, and the university approves that proposal or rejects it. For the students to agree, they have to hold a vote, right? So we have to strive a balance between what is fair and what people want. People want online exam, sure, because it is easier for them to cheat. Some people do not want an exam after all because, oh, I did fantastic on the midterm. I just wish that the midterm and assignment is the only thing that counts, right? So I can just walk out of this course with an easy 100. That's option 2, right? So, and the second option would be more fair than the first one. The second option would just be to waive the final exam. Everybody is going to have the exact same mark as they have right now. So the mark is only going to be assignments at midterm, right? So your current mark is our final mark. That is fair to everybody. That is super fair. It could not be any more fair. but how many people do actually want it? Right? So to be honest, it is just today that I have this idea of reducing the weight of the final exam. Before the tutorial, the hour before the tutorial, I had a chat with my DO1 instructor about this problem of how is the final evaluation is going to be. And the consensus that we agreed upon is to, if we're going to hold a final exam, we're going to reduce the weight. And the format of the final exam is going to be up to discussions. But if we're going to have a final exam, we have to reduce the weight. Right? And the entire idea of cheating will hurt yourself in the post one. Not really, because linear algebra, it depends on what you study. Depends on what you study. If you study math or statistics, if you don't know linear algebra, you're kind of screwed. If you study computer science, then maybe not. Especially theoretical computer science. Like, what's the point? Huh?
What did you say?
What's the point of linear algebra for theoretical computer scientists?
Graphics.
Theoretical computer scientists.
Theoretical. I don't think we use it. Well, we do use it in C37 or
Numerical algorithms.
Numerical analysis.
Uh-huh.
So it's like floating point numbers.
Uh-huh.
Right?
Uh-huh.
And stuff like
Yeah, it's just not as nearly as useful as you say in math or stats.
that. You also like use it for AI and machine learning.
That is more of a statistics problem more than a computer science problem. Yes.
I guess so.
Yes. Theoretical machine learning falls under statistics. So yeah, so that's what it falls up onto. But if you do computer graphics, I do know that computer graphics do use a lot of linear algebra. Right? Things like projections or like lighting and stuff like that. It's all just linear algebra. Projection matrix. Yeah, a projection matrix. Something called an idempotent matrix is a projection matrix. And it's a special type of matrix where P equals to P squared equals to P cubed equals to P to the power 4. So a matrix, when you multiply it by itself, it doesn't do anything, right? I do not know that you need to know linear algebra for C37. Your wonderful TA, Charles, says that you need linear algebra for C37, okay? So if you have any questions regarding that, yell at him, not me. I hold no responsibility for any related to computer science, as I know nothing about computer science. It is a subject I have a deep hatred against.
Your fourth year specialist in math?
Yes.
Like
comp sci. Well, what does comp sci?
Do we still have to take math P24? Yeah, you do. I think it's part of your specialist requirement for CS. Yeah.
P24, yes, P24 is something that you need to take as well. So yeah, in terms of determinant, I looked through assignment 5, I think. In terms of the assignment 5, the determinant part of assignment 5 is fairly easy. Let's just say. It is fairly easy, right? We can, yeah, so question 1, 2, 3, 4 are very easy. Now, in terms of eigenvectors is something that is, the eigenvectors is the last unit of this entire course. What eigenvector does is it takes a matrix and it sort of, in terms of computer science language, it's sort of compress it. It takes out everything that holds the information within the matrix and it discards everything else. Everything that holds the information of the eigenvalue of the matrix are what we call eigenvalues, right? And the vectors that holds the information of the matrix are called eigenvectors. So eigenvalues and eigenvectors are going to be the last unit of this entire course, and it is going to be a very important unit. When Kaidi starts to talk about eigenvectors and eigenvalues, make sure that you go to the lectures and pay attention, because it is important. In terms of the determinant part of the assignment, again, if you want to know some kind of property, all you have to do is to Google.
Eigenvectors are just the thing where you reduce everything to a diagonal, right?
Yeah, you reduce everything to basically what holds the information of the
And
matrix.
then you can square to make it.
No, that is called diagonalization. That is something different.
Okay. That's next.
That's B24 thing.
24. Okay.
Yes. Yes.
They're all mangled in my head now.
The diagonal matrix is not the eigenvalues.
Diagonalization.
Diagonalization, yes.
24.
Yeah. So eigenvectors are the vectors where, sorry, eigenvalues are the values which, if you multiply a vector to a matrix, it's the same as multiplying that value to the vector. So it kind of just reduced this entire matrix into a single number. Right? And there are many of these numbers together that holds all of the information that you can think about for the matrix. And all of these numbers together, they are called eigenvalues. And the vectors that satisfies this condition is called eigenvector. So there are vectors that
give us
enclose
a
all
head
the
start
information. I'll probably do that next week, not this week. Next Monday. Probably do that next Monday.
It's actually not.
You want to come and join me, Calvin?
You can't. You don't have access. The second you leave this room, you can't get back in.
Imagine if you leave right now and I forgot something, I'll just call you back. Just send that 38 around. Come back to campus. I mean, all of the social distancing that I can possibly want. I'm together with someone who hopefully does not have COVID-19. If he does, I think I'm already fucked.
No, I'm good.
And the entire journey that I walked here, I did not see anybody. So.
Oh, you walked here. You didn't take the bus. That's good.
I live 10 minutes away walking.
You
Well, am I just gonna take the bus for one stop?
Then you're fine.
Oh, here's back in Newmarket. Never mind. Question about a quotient space. Why does a vector space V/kernel V is excluding kernel V from V? Well, it is not excluding every vector in kernel V from V. What it does is for quotient space, you have the following property. So quotient space, what it kind of does is take a whole bunch of vectors that have some kind of equivalence relation, and it collapses it down to a single vector. So kernel of V didn't really get discarded. More or less, kernel of V just gets collapsed into 0. That is all. So if I have V divided by S, a vector space divided by some subspace, right? Then if I have a small s in S, S plus S is going to equal to 0 plus S. Right? So similarly for oh my god, the moment that you use the backside of the chalk, now I'm using it incorrectly all the time. V/kernel of X is the same thing, kernel of T, right? So if you have a vector V inside kernel of T, then V plus kernel of T is just going to equals to 0 plus kernel of T. So we didn't really discard it, but all we did is we collapsed every single vector inside kernel of T to 0. This is called an affine set. And the reason for that is because if you think of having a vector add a subspace as moving the subspace in some direction, then if you're moving the subspace in a direction that is already inside the subspace, did you really move it? Right? If I have R2 as my vector space, and I have S, which equals to XX as my subspace, if I move this entire subspace along a vector on S, did I really move it? It's the same as not moving. So every single one of the vectors on the subspace gets collapsed down to a single point in 0 because they're all the same. You did not move anywhere. You did not go anywhere. So it all got collapsed down to 0. Or another way of saying that would be for all v in kernel of v in kernel of t, v is equivalent with 0. Right? But this is something that is not in this course. You do not have to worry about that. Well, it is locked down. Yes, the campus is locked down. And because I have a special resource that I can use, I can still be on campus. We're going to do that next Monday, yeah?
Yeah.
Monday?
We're doing this next Monday?
Next Monday.
Depending what time.
2 to 4.
Got it. Might have to be later. Because I have to record 848 from 1 to 4.
At where? At home?
No, here.
Oh, they just have to open the door for me.
Oh, yeah, I can do that.
Yeah, just like take a 10-minute break or something.
I won't be here with you physically.
Yes, that's fine.
Then yeah, it should be possible.
Yeah. So for 3E4, do we have to prove that T is surjective? Well, for on 3E3, so on the third part of 3E, you already proved it is surjective, right? Because your codomain is the range of T, right? So if you prove that the range of T tilde is the same as the range of T, then you already have proved surjectivity. The third part of that of 3E is actually surjectivity. You do not need to prove it again, right? So sum 4, 3E. Let's just confirm what I said is correct. 3E3. Yes, 3E3 does show surjectivity. So you do not need to show it again. You don't have to show it again. You just have to show it in 3E3, and then for 3E4, the only thing that you have to do for 3E4 is well-definedness. Well-defined. The only thing that you have to do for 3E4 is to show it as well-defined. After you prove that it is well-defined, and then you combine with question 1, question 2, question 3 from 3E, then you can reach the conclusion of an isomorphism. Right? And the way that you prove, one, the linear map is just a typical definition of linear map. The way that you prove 2, injective, you can just prove that kernel contains only 0. For surjective, you have to pick a random element. For surjective, you have to show double set containment, right? Range of T tilde is a set. Range of T is a set. In order to show two sets are equal, you have to show that range of T tilde is a subset of range of T, and range of T is a subset of range of T tilde. Right? So that's that. Yes, you can.
Oh, go ahead. No, I actually want. Oh, do you want to sew? You want to sew? No. I have to. Yeah. Yeah, that's fine.
Yeah, that's fine.
Oh, okay.
13 minutes. All right, thank you. Am I going home after this? Yes, I'm leaving exactly at 4. Ending this at 4 and I'll just leave. If you have any questions, of course, you know where to reach me. You have my email, which is my preferred way of contacting me. If you do not want to use email,
You have WeChat?
Yes, I have WeChat, but it is my personal WeChat. I have a whole bunch of people adding me already. It is a little annoying. And Discord, you can also find me on Discord, but you have to find me on UTSC's Discord. You ask questions in UTSC Discord. You do not ask me through DM. No. Right. And if anybody are interested in the UTSC Discord, you can I can post an invite link. It's not the official Discord. It's a Discord made by a couple of comp sci people. All right, so that is the UTSC Discord, unofficial Discord. You can find me pretty active on there, I guess. When I wake up, I'm pretty active. When I'm asleep, I'm not at all active. Go figure, yes. I'll just, in my sleep, I'll just pull out my phone. I'll just be like, yeah, let's just reply to this question. Yeah, of course, that's what I'm going to do because I'm just that good. Any other question? I hope I am not setting an example for any one of you in home, self-isolating, okay? What I'm doing is not good as per definition of the government. So if you do not have a reason to leave, do not leave. Imagine, yes, imagine going out when there's COVID-19. Imagine right here, I do have a Blackboard at home, right? So the problem with the Blackboard at home is for two reasons. First is that Blackboard is of very low quality. So the lines that I make on that Blackboard, even with my very expensive $3 chalk, it's not a very solid line. It's not a very solid line, right? So that is one other problem. And in combination with the second problem, which is the fact that I do not have sufficient lighting at home. So right now, you see the board fairly clearly. It is because of the magnificent overhead lighting that shines directly on the board. You can see everything, right? But at home, there is no lighting whatsoever. So it's like it's like way darker than this. So it's very difficult to see stuff on a board, right? So without lighting and without a good board, I do not prefer to record anything on that board. That board is just for me to mess around. Whenever I have a math problem that I need to mess around with, instead of using paper, I just use that board. I can also record using a drawing tablet, but imagine doing math not on a blackboard. Like, that is just blasphemy. Wow. I have this. I have an iPad. I can do it on a tablet. I have a tablet, but it's, again, I don't want to do math not on a blackboard. It's just the idea of writing stuff, writing that the chalk that go through the surface of the blackboard, something about it just be so nice, right? Like when you do math on it, it's just natural. Natural. When you write stuff on the board, it's natural. When you write stuff on the iPad, it's not natural at all. Right? And disgusting Apple, sure, you can hate about Apple all you want, but in terms of a drawing tablet experience, I do not think that there is any tablet on the market that has a better pen than the Apple Pencil. Okay? Paid promotion, yes. This is the only Apple product that I have because I truly believe that the only decent product that Apple make is their iPad. Everything else about Apple just suck, right?
He's a sellout.
I'm a sellout, yes. Go to my Amazon affiliated link and get your own iPad today. Not sponsored by Apple. I do not have a Surface. I have a laptop. There's a ThinkPad. And even the Lenovo pen is actually not very good. So Lenovo pen is not very good. Surface pen is also not very good compared to the Apple Pencil. The Google pen, ugh. I tried it in a store once, and the delay on that thing is just, oh my god. And the other companies like HP or Acer, their tablet computers are just, yeah. What do you mean, of course, I have a ThinkPad? And what do you mean I'm sponsored by Raid Shadow Legend?
NordVPN as well.
This video is sponsored by Squarespace. Get your own trial today at squarespace.com/Jerry. Well, don't do CES then. Do something that is far superior. Have you heard of a program called mathematics? Just do pure math. Much easier post to hit. Or you can do stats. Stats is more applicable. You can do quantitative finance. You can do machine learning. Right after you graduate in quantitative finance, it's a pretty easy. Yeah, you have a pretty easy start, like a 6-figure start or something like that. Quantitative finance is a very, very rich field. Of course, that is based on if people is actually going to hire you, right? Machine learning is okay, I guess. I don't really care about computer science, anything related to computer science. My research direction is probably going to be on theoretical stats. Yeah, that is pretty ironic. That is actually very ironic. Pro Minecraft player. I don't know. The entire idea of I shouldn't be posing my view onto you people, so I'm not gonna talk about it. My opinion is worthless. A pro streamer. I'm not a pro streamer. I do stream. I do have a Twitch channel, but you probably won't find it. And I don't stream on it as often. Well, pretty much at all nowadays. Maybe stream it from like once or twice every month. Yes, I am streaming right now and I'm getting paid. Again, sponsored by the University of Toronto, Scarborough, the best campus of all three. That part I do believe. The last sentence is true. Although the first sentence, you know what, whatever. UTSC a lot more than UTSG. You know how much work, you know how much less work I have to do if I can do it on Twitch? Like it would be so much less work. I just have my phone on a tripod and I just hit go live and there, done. Instead of setting up this entire like Blackboard collaborate with I have to find a way to connect the camera on my phone to the screen, with which a capture card doesn't even work for some reason. I have to. It's just so much work. It's fine that I get paid for this at the very least. All right, one more minute. If you don't have any more questions, you can leave now. Or you could have left like half an hour ago. Well, yeah, I didn't have 2 hours worth of material to go through because again, determinant. What am I going to talk about determinant? The properties. What's the point? Right? What's the point? You can find all of those properties online. They are very easily proven. You don't really learn too much things from proving them. You just basically learn how to calculate determinant. That's what you learn. That's about it. Although I do think that quotient mapping, or what quotient says, or quotient space is a lot more useful, a lot more fun, and a lot more hard as well. Like I can do the theoretical version of quotient mapping. I'm going to do the theoretical version of quotient set. So it does. You can divide any two sets instead of. You can divide a set against the equivalence relation instead of dividing two vector spaces like that. I think that is more cool. All right. I'm just going to call it here a day. If you have any questions, you have Fridays 2 hour from 2 to 4 on Blackboard Collaborate. And if you have any questions between now and then, you can send me an email. I will try to reply everybody's email within a single hour. And again, please don't send me an email on things like, oh, I don't know how to do question 1, 2, 3, 4, 5, 6. I'm not going to spend an entire essay on replying to a single email. So try to keep it to short conceptual questions. If you have any longer questions, you should try to keep it until the office hour. Our assignment is due on Sunday, so remember to do that. And that's it. So thanks for joining. Goodbye.